TeX but often pronounced tekh in English, is a typesetting system designed and mostly written by Donald Knuth and released in 1978. Within the typesetting system, its name is formatted as TeX. Together with the Metafont language for font description and the computer modern family of typefaces, TeX was designed with two main goals in mind: to allow anybody to produce high-quality books using a reasonably minimal amount of effort, and to provide a system that would give exactly the same results on all computers, at any point in time. TeX is a popular means by which to typeset complex mathematical formulae. It has been noted as one of the most sophisticated digital typographical systems in the world. TeX is popular in academia, especially in mathematics, computer science, economics, engineering, physics, statistics, and quantitative psychology. It has largely displaced Unix Troff, the other favored formatter, in many Unix installations, which use both for different purposes. It is also used for many other typesetting tasks, especially in the form of latex, context, and other template packages. The widely used MIME type for TeX is Application, ʻtɛx. TeX is free software. History. When the first volume of Donald Knuth's The Art of Computer Programming was published in 1969, it was typeset using hot metal typesetting set by a monotype corporation typecaster. This method, dating back to the 19th century, produced a good classic style, appreciated by Knuth. When the second edition of the second volume was published, in 1976, the whole book had to be typeset again because the monotype technology had been largely replaced by phototypesetting, and the original fonts were no longer available. When Knuth received the galley proofs of the new book on 30 March 1977, he found them awful. Around that time, Knuth saw for the first time the output of a high-quality digital typesetting system, and became interested in digital typography. The disappointing galley proofs gave him the final motivation to solve the problem at hand once and for all by designing his own typesetting system. On 13 May 1977, he wrote a memo to himself describing the basic features of TeX. He planned to finish it on his sabbatical in 1978, but as it happened the language was not frozen until 1989, more than 10 years later. Guy Steele happened to be at Stanford during the summer of 1978, when Knuth was developing his first version of TeX. When Steele returned to MIT that autumn, he rewrote TeX's I/O to run under the its operating system. The first version of TeX was written in the Sale programming language to run on a PDP-10 under Stanford's Waits operating system. For later versions of TeX, Knuth invented the concept of literate programming, a way of producing compilable source code and cross-linked documentation typeset in TeX from the same original file. The language used is called Web and produces programs in DEC PDP-10 Pascal. A new version of TeX, rewritten from scratch and called TeX82, was published in 1982. Among other changes, the original hyphenation algorithm was replaced by a new algorithm written by Frank Liang. TeX82 also uses fixed-point arithmetic instead of floating-point, to ensure reproducibility of the results across different computer hardware, and includes a real, Turing-complete programming language, following intense lobbying by Guy Steele. In 1989, Donald Knuth released new versions of TeX and metafont. Despite his desire to keep the program stable, Knuth realized that 128 different characters for the text input were not enough to accommodate foreign languages. The main change in version 3.0 of TeX is thus the ability to work with 8-bit inputs, allowing 256 different characters in the text input. Since version 3, TeX has used an idiosyncratic version numbering system, where updates have been indicated by adding an extra digit at the end of the decimal, so that the version number asymptotically approaches pi. This is a reflection of the fact that TeX is now very stable, and only minor updates are anticipated. The current version of TeX is 3.14159.265. It was last updated the 12th of January 2014. The design was frozen after version 3.0, and no new feature or fundamental change will be added, so all newer versions will contain only bug fixes. Even though Donald Knuth himself has suggested a few areas in which TeX could have been improved, he indicated that he firmly believes that having an unchanged system that will produce the same output now and in the future is more important than introducing new features. For this reason, he has stated that the absolutely final change will be to change the version number to pi, at which point all remaining bugs will become features. Likewise, versions of ʻtɛx after 2.0 asymptotically approach E, and a similar change will be applied after Knuth's death. Since the source code of TeX is essentially in the public domain, other programmers are allowed to improve the system, but are required to use another name to distribute the modified TeX, meaning that the source code can still evolve. For example, the Omega project was developed after 1991, primarily to enhance TeX's multilingual typesetting abilities. Donald Knuth himself created unofficial, modified versions, such as TeX, which allows a user to mix texts written in left-to-right and right-to-left writing systems in the same document. Typesetting system. TeX commands commonly start with a backslash and are grouped with curly braces. Almost all of TeX's syntactic properties can be changed on the fly, which makes TeX input hard to pass by anything but TeX itself. TeX is a macro and token-based language. Many commands, including most user-defined ones, are expanded on the fly until only unexpandable tokens remain, which are then executed. Expansion itself is practically free from side effects. Tail recursion of macros takes no memory, and if-then-else constructs are available. This makes TeX a Turing-complete language even at the expansion level. The system can be divided into 4 levels. In the first, characters are read from the input file and assigned a category code. Combinations of a backslash followed by letters or a single other character are replaced by a control sequence token. In this sense, this stage is like lexical analysis, although it does not form numbers from digits. In the next stage, expandable control sequences are replaced by their replacement text. The input for the third stage is then a stream of characters and unexpandable control sequences. Here characters get assembled into a paragraph. TeX's paragraph breaking algorithm works by optimizing breakpoints over the whole paragraph. The fourth stage breaks the vertical list of lines and other material into pages. The TeX system has precise knowledge of the sizes of all characters and symbols, and using this information, it computes the optimal arrangement of letters per line and lines per page. It then produces a DVI file containing the final locations of all characters. This DVI file can be printed directly given an appropriate printer driver, or it can be converted to other formats. Nowadays, PDF TeX is often used, which bypasses DVI generation altogether. The base TeX system understands about 300 commands, called primitives. These low-level commands are rarely used directly by users, and most functionality is provided by format files. Knuth's original default format, which adds about 600 commands, is plain TeX. The most widely used format is LaTeX, originally developed by Leslie Lamport, which incorporates document styles for books, letters, slides, etc., and adds support for referencing and automatic numbering of sections and equations. Another widely used format, TeX, is produced by the American Mathematical Society and provides many more user-friendly commands, which can be altered by journals to fit with their house style. Most of the features of TeX can be used in LaTeX by using the AMS packages. This is then referred to as AMS LaTeX. Other formats include context, used primarily for desktop publishing and written mostly by Hans Hagen at Pragma. How TeX is run. A sample Hello World program in plain text is Hello World by % marks the end of the file, not shown in the final output. This might be in a file myfile.txt, as .txt is a common file extension for plain text files. By default, everything that follows a % on a line is a comment, ignored by TeX. Running TeX on this file will create an output file called myfile.v, representing the content of the page in a device-independent format. Knuth has said that there is nothing inherent in TeX that requires DVI as the output format, and later versions of TeX, notably PDF TeX, ʻtɛx and ʻtɛk, all support output directly to PDF. Mathematical example TeX provides a different text syntax specifically for mathematical formulas. For example, the quadratic formula appears as the formula is printed in a way a person would write by hand, or typeset the equation. In a document, entering mathematics mode is done by starting with a dollar symbol, then entering a formula in text syntax, and closing again with another of the same symbol. Knuth explained in Jest that he chose the dollar sign to indicate the beginning and end of mathematical mode in plain text because typesetting mathematics was traditionally supposed to be expensive. Display mathematics is similar, but uses $$ instead of a single dollar symbol. For example, the above with the quadratic formula in display math. Novel aspects. The TeX software incorporates several aspects that were not available in, or were of lower quality in, other typesetting programs at the time when TeX was released. Some of the innovations are based on interesting algorithms, and have led to several theses for Knuth's students. While some of these discoveries have now been incorporated into other typesetting programs, others, such as the rules for mathematical spacing, are still unique. Mathematical spacing. Since the primary goal of the TeX language is high-quality typesetting for publishers of books, Knuth gave a lot of attention to the spacing rules for mathematical formulae. He took 3 bodies of work that he considered to be standards of excellence for mathematical typography. The books typeset by Addison Wesley Publishing's House, in particular the work of Hans Wolff and Joseph Louis Lagrange, editions of the mathematical journal Acta Mathematica dating from around 1910, and a copy of Indagationes Mathematicae, a Dutch mathematics journal. Knuth looked closely at these printed papers to sort out and look for a set of rules for spacing. While TeX provides some basic rules and the tools needed to specify proper spacing, the exact parameters depend on the font used to typeset the formula. For example, the spacing for Knuth's computer modern fonts has been precisely fine-tuned over the years and is now set, but when other fonts, such as AMS Euler, were used by Knuth for the first time, new spacing parameters had to be defined. The typesetting of math in TeX is not without criticism, particularly with respect to technical details of the font metrics, which were designed in an era when significant attention was paid to storage requirements. This resulted in some hacks, overloading some fields, which in turn required other hacks. On an aesthetics level, the rendering of radicals has also been criticized. The OpenType math font specification largely borrows from TeX, but has some new features, enhancements, hyphenation and justification in comparison with manual typesetting. The problem of justification is easy to solve with a digital system such as TeX, which, provided that good points for line breaking have been defined, can automatically spread the spaces between words to fill in the line. The problem is thus to find the set of breakpoints that will give the most pleasing result. Many line-breaking algorithms use a first-fit approach, where the breakpoints for each line are determined one after the other, and no breakpoint is changed after it has been chosen. Such a system is not able to define a breakpoint depending on the effect that it will have on the following lines. In comparison, the total fit line breaking algorithm used by TeX and developed by Donald Knuth and Michael Plass considers all the possible breakpoints in a paragraph, and finds combination of line breaks that will produce the most globally pleasing arrangement. Formally, the algorithm defines a value called badness associated with each possible line break. The badness is increased if the spaces on the line must stretch or shrink too much to make the line the correct width. Penalties are added if a breakpoint is particularly undesirable. For example, if a word must be hyphenated, if two lines in a row are hyphenated, or if a very loose line is immediately followed by a very tight line. The algorithm will then find the breakpoints that will minimize the sum of squares of the badness of the resulting lines. If the paragraph contains possible breakpoints, the number of situations that must be evaluated naively is. However, by using the method of dynamic programming, the complexity of the algorithm can be brought down to. Further simplifications lead to an efficient algorithm whose running time is almost always of order. A similar algorithm is used to determine the best way to break paragraphs across 2 pages, in order to avoid widows or orphans. However, in general, a thesis by Michael Plass shows how the page-breaking problem can be NP-complete because of the added complication of placing figures. TeX's line-breaking algorithm has been adopted by several other programs, such as Adobe InDesign and the new FMT Unix command line utility. If no suitable line break can be found for a line, the system will try to hyphenate a word. The original version of TeX used a hyphenation algorithm based on a set of rules for the removal of prefixes and suffixes of words, and for deciding if it should insert a break between the two consonants in a pattern of the form vowel-consonant, consonant-vowel. TeX 82 introduced a new hyphenation algorithm, designed by Frank Liang in 1983, to assign priorities to breakpoints in letter groups. A list of hyphenation patterns is first generated automatically from a corpus of hyphenated words. If TeX must find the acceptable hyphenation positions in the word encyclopedia, for example, it will consider all the subwords of the extended word encyclopedia, where is a special marker to indicate the beginning or end of the word. The list of subwords includes all the subwords of length 1, of length 2, etc., up to the subword of length 14, which is the word itself, including the markers. TeX will then look into its list of hyphenation patterns, and find subwords for which it has calculated the desirability of hyphenation at each position. In the case of our word, 11 such patterns can be matched, namely 1C4L4, 1Ψ, 1D4I3A, 4ED, E3D, 2I1A, OP5D, 2P2Ed, 3PED, Pedia4, Y1C. For each position in the word, TeX will calculate the maximum value obtained among all matching patterns, yielding N1Ψ1C4L4O3P4E5D4I3A4. Finally, the acceptable positions are those indicated by an odd number, yielding the acceptable hyphenations N-Ψ-CLOP-DIA. This system based on subwords allows the definition of very general patterns, with low indicative numbers, which can then be superseded by more specific patterns if necessary. These patterns find about 90% of the hyphens in the original dictionary. More importantly, they do not insert any spurious hyphen. In addition, a list of exceptions are included with the plain text format. Additional ones can be specified by the user. Metafont, not strictly part of TeX, is a font description system which allows the designer to describe characters algorithmically. It uses Bezier curves in a fairly standard way to generate the actual characters to be displayed, but Knuth devotes lots of attention to the rasterizing problem on bitmapped displays. Another thesis by John Hobby further explores this problem of digitizing brush trajectories. This term derives from the fact that metafont describes characters as having been drawn by abstract brushes. It is commonly believed that TeX is based on bitmap fonts but, in fact, These programs know nothing about the fonts that they are using other than the dimensions. It is the responsibility of the device driver to appropriately handle fonts of other types, including PostScript Type 1 and TrueType. Computer Modern is freely available in Type 1 format, as are the AMS math fonts. Users of text systems that output directly to PDF, such as PDF TeX, ʻtɛx, or LuaTeX, generally never use metafont output at all. Macro language TeX provides an unusual macro language. The definition of a macro not only includes a list of commands but also the syntax of the call. Macros are completely integrated with a full-scale interpreted compile-time language that also guides processing. TeX's macro level of operation is lexical, but it is a built-in facility of TeX that makes use of syntax interpretation. Comparing with most widely used lexical preprocessors like M4, it differs slightly, as the body of a macro gets tokenized at definition time. That is, it is not completely raw text. Except for a few very special cases, this gives the same behavior. The TeX macro language has been successfully used to extend text to, for instance, latex and context.